So hello and welcome back. So up to this point in the semester, we've been talking about electricity, we've been talking about magnetism, and in our last lecture, we talked about how electricity and magnetism are really two forms of the same thing. There's no difference. The magnetism is a relativistic effect from what we also call electricity. So it doesn't make sense to talk about really electricity and magnetism as two separate things. Instead, we call them electromagnetism. But one of the things we found was that if we take the last two of the Maxwell equations and we combine them, then we can solve for either the electric field or the magnetic field, doesn't matter which. And what you find is that you get a second order partial differential equation in time and space. And the form of that equation has a very well known solution. It's called the wave equation. And with that, we were able to prove that an oscillating electromagnetic field propagates through space. And by looking at the speed at which that wave propagates, we realized that electromagnetic waves are simply light. And while we derived it for radio in the case of an RLC circuit, radio is light just like visible is light. All of these different types of light really are nothing more than electromagnetic fields that oscillate at different frequencies and have different wavelengths. And we'll get into that more in detail later on. What we want to look at today is suppose we have one of these propagating electromagnetic fields. And one way you can think about it is, imagine you've got a sheet and it's flat. And so that's space. And it's also my electric field in space before I have any kind of disturbance. And then I take it and I shake the sheet. You're going to get this wave that moves through the sheet and carries out off into the universe. So just by oscillating here with my hands, I can create an effect later on down the road. So there's not really any such thing as light rays or anything like that. What we really have is simply that sheet, that wave, traveling through space and time from that. So we're going to talk about the idea of polarization, and this may be something that's familiar to you. It may not be. Surely, though, most of you have polarized sunglasses. So we're going to learn how those work today. It's not that complicated, really, when we're coming in here. Polarization is simply really just the orientation of the electric field and the magnetic field. I'm going to show you some pictures about that in just a minute that'll make that really clear. So let's get into it. Let's get started. All right, so pull out your book and take a look at the polarization section because, as we all know, I can't draw in 3D, so we've got these nice computer-generated diagrams that I've made here. This really, when we start talking about electromagnetic waves, we can't avoid working in 3D. And as you know, the electric field and the magnetic field have to be at right angles to each other. They have to be perpendicular to each other. And so what we've got here, if I switch to my pen, let's get the black pen going. Then I've got my electric field here and my magnetic field here. The electric field is going, in this case, up and down like this, whereas the magnetic field is going left and right. So see if you can kind of visualize what that is. And it's traveling through space. It's traveling in this direction. It's propagating, we call that. So both of them are at right angles to each other. But there's nothing that says that the electric field has to be up and down. And in fact, if you look at the picture that we have down here, we've got it rotated. So now the electric field is going left and right, and the magnetic field is going up and down. Now, notice something very carefully here. We did not simply just swap them because that would violate our right-hand rule. What we have to do is we have to actually rotate them. And so try to think about that spatial visualization rotation in your head there. So the magnetic field was lying to the side and the electric field was upright. So when we rotate it then so that the magnetic field is upright, the electric field must actually be on the opposite side from what the magnetic field is. Now, I've done a 90-degree rotation here, but we could do any rotation. And in fact, if I have a light source, an electromagnetic wave source, all possible polarizations are going to be available. So they're not just going to be oriented here and here, it's going to be here and then all possible angles in between with that. So all of those are existing all at the same time. And while that might be interesting, you wouldn't think that it would be terribly useful. And it wasn't until about 1932 when a engineer named E.H. Land, who was actually working for Kodak, the camera company, discovered a material that was made out of long chain polymers that he had mixed with iodine so that they would interact with an electric field from that. And so if we're going to sketch what that looked like, I might have these long chain polymers. A polymer is, well, most plastics are made out of polymers, but they can be organic molecules, often are. And but we can get very, very, very long molecules, individual molecules that are like this. But what he noticed with this is that an electric field, I'm going to change color here, an electric field that came at it this way would get absorbed. So if imagine my fingers are the long chain polymers, if the magnetic field came at it this way, then it would get absorbed by the polymer chains. On the other hand, if I had a magnetic field, let's change colors. If I had a magnetic field or electromagnetic field that was going this way, side to side, so again, here's my polymers, and here's that wave this way, it would actually pass through unimpeded without any problem at all. So what this material does is it only allows one polarization to pass through it. And so he named it a Polaroid. And if you've ever heard of a camera, that's what Polaroid film is made out of. It's made out of these Polaroids with that. So anything moving through this Polaroid has exactly one polarization. Now, you may say, well, wait a minute, Dr. K, didn't you just say that we could be at any angle? And we absolutely can. But remember, though, that any vector, so any orientation, any angle vector that I have here, can be broken down into a horizontal and a vertical component. So let's just redraw this here so we can kind of see what we're talking about. So here's my long chain polymer here, right? And let's suppose that I've got some wave coming in at some arbitrary angle. And we'll say that this is the angle of the polarizer. We can often draw this vector arrow to indicate the angle of the polarizer itself. So if I have another incoming wave that has maybe this polarization, and again, I'm trying to draw it in 3D, but we're doing the best we can here. So it's coming in at some angle. But I can break that into a component that is perpendicular and parallel to the long chain polymer, to the Polaroid. What that means then, of course, is that the perpendicular component will make it through, but the parallel won't. So no matter which orientation the light ray, the electromagnetic wave comes in at, it's going to only allow one polarization to come through. The other part of it, the other vector part of it, is going to cancel out. So as a result, 1/2 of the light will end up being able to be transmitted. So any wave I can break down into those components. The half that ends up being perpendicular right here, or perpendicular to my Polaroid, that is, it's going to make it through. The ones that are parallel to the Polaroid, though, are going to get blocked. So this is what makes sunglasses work. What makes your polarized sunglasses work is that even if they're absolutely clear, that the material in the polarizing of your lenses there only allow one polarization of light to come through. So you've got all these random waves coming at you, but only one polarization is going to come through. So right off the top, you've cut down the amount of light that's reaching your eye by 1/2. And so the light doesn't seem as bright from that. So the nice thing about that is that it can do it without actually changing the color of the light necessarily or anything along those lines. So they're very valuable. And of course, here in Arizona, we have a fairly high incidence of cataracts, not just because of Sun City, but also because of the amount of UV radiation we get. So some people think, oh, well, I'll get polarized sunglasses to protect me from the UV, but that's a completely different process. You really should make sure that your sunglasses also have 100% UV block. If it's less than 100%, throw them away, because if they are tinted at all, then your pupils are going to dilate. So let's say they block 90%. Well, but your pupils are so much larger that you're actually taking in a lot more of those UV rays, and the polarization isn't going to help that. So the polarization only reacts to certain wavelengths. And so in this case, we're only looking at the visible wavelength, not at the UV wavelength. So keep in mind that they are entirely separate things. Now, sometimes there's a bit of false advertising. If you go to a department store, Walmart, Target, something like that, and you pick up just a cheap pair of sunglasses, it may say they're polarized, but are they really? So let's think about how we could prove whether or not these sunglasses are actually polarized. So I'm going to go ahead and get rid of this one. Take a look at microtask 1 here. And what I want you to do is I want you to pause the video and think about this, because this is another one of those conceptual things. We're going to get to an equation at the end, yes. But it's important that you understand the concept of what's going here. And the only real way to do that is to just sit down and work it out. So what I want you to do is pause the video and work all the way through microtask 1. Trust me, it's going to help you. So make sure that you do that. Pause the video now. Okay, did you work it out? I know some of you are like, no, I don't need to work it out. I'm going to keep going. Yes, you do. All right, so we'll talk about it then. So going back to my pen. So here I've got 2 polarizers, and you can imagine, suppose I have 2 polarized sunglasses. So I'll do my crude little sunglass drawing here. Yeah, those are sunglasses. Can't you tell? You know, there's the earpiece, right? So what if the polarizer in those lenses is oriented this way? Then only the light that has this cross polarization, this perpendicular polarization, is going to make it through. All right, now suppose I take 2 of those glasses, and we'll make a red one here. And let's suppose that I put the lenses right on top of each other. So here's my other pair of sunglasses. Now these also have the same polarization. So it's oriented in exactly the same way. So that's what we're trying to draw in this diagram here in microtask 1 right here. Okay, so what's going to happen to the intensity of the light when it passes through the first Polaroid? So let's imagine that I have, intensity by the way means brightness. We'll more formally define it here in just a second. But suppose I have an electric field, and this is my original oscillating electromagnetic field that's coming in, and it hits this polarizer. What do I get out? What percentage of the light is going to come out? Half, right? All the polarizers, as we said, they're going to only allow half to go in. In this particular case, it's going to block the up-down polarization, and it's going to allow the left-right polarization to come through. So we're going to call that E0. And while that's a little confusing for some students because they want to say, oh, wait, E0 should be my original light. It's not, that's not how it's defined. And remember, you can define the symbol any way you want, but we do need to stay with what's with the traditional. So one thing you can do right here then, so the intensity of light when it passes through the first Polaroid is going to be 1/2. So E0 is going to equal 1/2 of my original amount of electric field that's coming through here. All right, so half of the energy is going to be absorbed. All right, so what now? Think about this one, because this is where it starts to get important, because we're really talking about the interaction between these 2 polarizers. What's going to happen to the amount of light, the intensity of the light? Remember, light is an electromagnetic wave. What's going to happen to it when it passes through the second Polaroid? Nothing. Because the only light that comes through here has this left-right polarization, right? However, the second polarizer also allows that left-right polarization to go through. So while half of it got cut out here at this first one, what's left makes it through all the way without any trouble at all. And so the answer here is nothing happens to it. So the amount, my E, and we'll make these vectors because the E field should be a vector. The E, or E final, some people will write that as, E is simply going to be equal to E0. So the amount of light that comes in here. Now remember, E0 though is half that original. All right, so now suppose that we rotate our sunglasses 90 degrees. So let's see if we can draw that. So here's my first polarizer, my first polarized sunglasses, and there's the earpiece there, and there's the earpiece there, and it's oriented this way. Now, you can do this in the store. Take 2 pairs of polarized sunglasses and see if they actually are. But when they're like this, you should be able to see through them. Then rotate the lens like this. And that's what we're showing in this picture here. So I'm going to try to sketch that. So now my lens looks like this. And there's my earpieces, right? And my polarizer is oriented this way. Okay, so that's what we're trying to draw in this image here. So we've rotated that second polarizer by 9 degrees. Now, I don't want to blast through that because that's an important thing. When we talk about the angle, the angle theta through with this, we're talking about the angle between the polarizers. or between the Polaroids. So we're not talking about the angle that it hits that first lens or that it hits that first Polaroid. We're talking about the relative angle of the polarization vectors between the two lenses. So in the top picture, our polarization lens vectors are completely lined up, so the angle is 0. Here, our polarization vectors are at right angles to each other, so the polarization vector is going to be 90. So what will happen to the intensity of the light when it passes through the first Polaroid? Well, it's still going to be half, right? It's going to be half of our original. So here I've got my original light, my original EM wave that's coming this way. And then what comes out is going to be E0. That's going to be what passes through the first Polaroid. So E0 then is again equal to 1/2 of my original light. Now, what's going to happen to the intensity of the light when it passes through the second polarizer? Think about it. It's going to be gone. So the intensity will actually go to 0. And let's think about why. So I've got all possible polarizations coming this way, but only this polarization is going to survive here. But that left-right polarization can't make it through the second polarizer. And so no light at all gets transferred. So if you're doing this test in Target or Walmart or whatever, you take your lenses, you should be able to see through them like this. If you rotate by 90 degrees, everything should go completely black. You should not be able to see through it at all. If you can, they're not polarized sunglasses. And so you need to just put them back and find something different. And I've done this before. And sometimes some of the sunglasses that are marked polarized are not actually polarized. But it's a very simple test to do. Just take 2 of the identical ones, put them on top of each other, rotate one of them by 90 degrees, and you should be able to see, I can see through and it fades out. I can see through and it fades out. So here we can see that the amount of light that passes through the polarizers depends upon that angle, that theta between them. So think about it then, based on what we've done up here. What is the relative angle that allows the most light to pass through? Well, as we said, that's going to be 0 degrees, right? So when the 2 polarizers are lined up, so when the polarization vectors are lined up, then the angle between them is 0. We're not talking about the angle hitting the lens. We're talking about the angle between the polarizers, not talking about the angle of the light at all. So what's the relative angle that allows the least light to pass through? Well, as we saw, that's going to be 90 degrees. And this is what physicists do all the time. We do the experiment, we look at this, and now we say, okay, now I want a mathematical representation of the physical reality with this. And so one of these trig functions would have a maximum at 0 degrees and a minimum at 90 degrees. Which one? Stop and think about it. Well, that's going to be the cosine. So cosine of 0 is going to be 1. Cosine of 90 is going to be 0. So we know that our function then has to depend upon the cosine of theta, the angle between our polarizers. When my angle between my polarizers is 0, I get 100% of the light that passed through the first polarizer. Don't be confused by that. It's not 100% of the incident light, of the original light. It's 100% of the light that passed through the first polarizer. If it's at 90 degrees, well, then of course it's 0. But now we see that if I'm at any angle in between, I will get a different amount. So for example, if I'm at 45 degrees, then 50% of the light that passed through the first polarizer will make it through. And so I can adjust that by adjusting that angle. And if you take your sunglasses, you can see that. It doesn't just go from light to black. Instead, it fades, and you'll be able to see that. All right, so given that, we now know what we need in order to come up with our equation. So let's scroll up here to where we can do this. So hopefully you've already done this. Hopefully you paused the video and you worked it out. But let's think about it. We know that I want to know what is my final amount of electric field. And I'm being careful to draw the vector here because we're talking about energy. And I know that then that's going to be the amount that makes it through the first polarizer, E0, times the cosine of the angle between the polarizers. So stop and think if that makes sense. Now, some people are like, no, I want to write this in terms of my original. And you could, because remember that E0 is always going to be half of my original. But this is the traditional way because ultimately we can't control how much light is coming through. We don't know what E original is most of the time, but we can control what percentage of it is going to pass through. And that's really what we're getting. Okay, now we mentioned intensity before, so let's define that kind of precisely because we're going to be using that fairly often here. Intensity is the amount of energy, the amount of power that's hitting a square meter of a certain substance. Okay, so the more energy I have shining on this at a faster rate, then the more intensity that I say I have. And it's actually something that's very easy to measure. Measuring electric field is a little challenging because remember, the only way we know how to do it is to measure some sort of voltage changing there. But in this case, I can actually clip a little temperature sensor to a black screen, and as that electromagnetic wave comes through, light, then that energy is going to get absorbed by the screen, and that's going to get converted into temperature at a certain rate. And so given that, then I can figure out what is the intensity of light shining on there, and it's actually very easy. We're not going to go through all the details, but the intensity varies as the square of the electric field. And if you think about it without even having to work out all the details, that kind of makes sense, right? Because I'm talking about an area here. So I've got a meter squared involved in there, and the details are a little more involved in that. But hopefully you can accept then that it's going to be the square of the electric field. So if I'm going to express this mathematical expression here in terms of the intensity, then all I need to say is the measured intensity, which is not a vector, there we go, is going to be equal to the amount of light, the intensity of the light that made it through the first polarizer, but now it's got to be cosine squared theta, right? Because I is proportional to E squared from that. And so this relationship right here is called Malice's law. And this expresses the amount of intensity, the percentage of intensity that you're going to get moving through those two polarizers based on the angle between those two polarizers. Now, this is a very important relationship, and it's something that we're going to use far more often than we're going to use the electric field here. But if I needed the electric field, well, I know it's going to be proportional to that intensity here. I'm going to pause for just a minute. We've used a lot of I's over the past several semesters, right? So we've talked about the moment of inertia. We've talked about the impulse. Recently, we've been talking about the current. Now we've got the intensity, and all of them are I. And so there's no way in most cases to distinguish between the two of them. You have to look at the context and you have to understand what your symbols mean. This is why in our step 3, we always define our symbols, because it could be anything. And this also means if you're taking an exam or you're working a problem or you're actually out in the field doing your job, don't just go through your flip book and find, oh, here's an equation with I. That must be what I need. Because it may not be. In this case, you've only got a 25% chance of it being what you need. So make sure that you're keeping up in your flip book with what each of these symbols means. In this case, I is the intensity, not the current. All right, so pause the video for a minute. Make sure that you've kind of got a good handle on the theory behind that. It's not complicated, but there is a lot that we have to think about with this spatial transformation going on. Let's talk about a couple of applications to this. The most common that you're going to see is an LCD screen. And I'm sure all of you have at one time or another seen an LCD screen. Your calculator probably has one. These work because of polarization. And so I'm going to zoom in on the diagram that we have here. So we're looking at it from the side. Let me get my pen here. So we're looking at this from the side. So here's my eye, and I'm looking down on my calculator, for example. And this cell represents 1 pixel on it. So here I've got an up-down polarizer, and then some liquid, and a left-right polarizer here. Now, the LCD does not provide any light on its own. You've probably seen this. If you're in a dark room, you can't see it. It's not going to show anything. And so a lot of things will have a backlight that will shine across, basically. It'll shine across those pixels, and that's what will light it up. But left to itself, it emits no light whatsoever. Instead, there's the ambient light around you. So, you've got some sort of light bulb behind you. That light ray, remember, there's no such thing as a light ray, is an oscillating electromagnetic field. So here I've got an up-down polarizer. Now, all possible polarizations are here. So only the left-right polarization is going to make it through that up-down polarizer. Now, this liquid, when it has no voltage at all, when no voltage is running, no current is running through that liquid, it has a property that it rotates the polarization by 90 degrees. So as I come through the first polarizer, only the left-right polarization is surviving. However, the liquid is rotating that left-right so that it's going up and down. Now when the wave reaches this left-right polarizer over here, instead of going left-right, it's now going up and down. And so it can pass through it. Then I've got a mirror on the bottom of the pixel here. So the pixel consists of a polarizer, the liquid, another polarizer, rotated 90 degrees, and a mirror. When the light hits the mirror, now remember at this point, it's going up and down. It hits the mirror and it reflects and it comes back and it's still going up and down. So it can pass through the left-right polarizer with no problem. The liquid then rotates it 90 degrees again so that now it's going left-right. And so now it can get through the up-down polarizer. And so we get light back at your eye. So this makes the pixel look bright to you. So if there's no kind of voltage, no kind of current going through it whatsoever, then the pixel looks white. So the only time that I'm going to get a dark pixel, and that's going to be down here, let's move our screen so we can see it, is if there is a voltage applied to it. If there is a voltage applied to the liquid, then the polarization doesn't rotate. So once again, I'm going to have my light source over here. And let's say that I have this left-right polarization is the only one that's going to make it through that polarizer. But because it doesn't rotate it, when it hits that left-right polarizer, it's absorbed. Nothing hits the mirror, nothing comes back at you. So if this is, again, is your eye right here, if nothing's coming back at you, then it looks dark. And so I can control each pixel by making it, turning on the voltage, it becomes dark. Turn off the voltage, it becomes white. And LCDs are very energy efficient because the only time that I need to, the only energy I'm spending is for my actual dark pixels that I'm drawing on there. If any other kind of monitor, television monitor, computer monitor, LEDs, LED screens, LED TVs, all of these pixels all have to be lit at the same time and they have to be maintained lit all the time. Otherwise, they just go out. With the LCD screen, you're only spending the energy for the actual pixels that you want to be black. Any other time, most of the screen is going to be white, and it's not requiring any energy, any electricity whatsoever to keep going. So this is why LCDs are so common, because they're so energy efficient. This is a direct application, then, of this idea of Malice's law and the polarization. There's a similar one. There is a type of glass that can have its polarization rotated electrically, very similar to the liquid crystal. And so it's a double pane window. And then the first window is just a standard polarizer. So, maybe it'll be in the direction that my fingers are pointing now. You can rotate the polarization by turning a knob of this second piece of glass. So as long as the two are aligned, then light's going to pass through. Now it's still going to block half the light, but that's not a bad thing, right? That's going to reduce the amount of sunlight that's coming, even if you have your windows open or your curtains open. In this case, though, you don't need curtains, because what you do then is you turn the dial and you rotate the polarization of that second pane. Now how much light is making it through? None. And so the window goes completely black. And so you're able to close the curtains without actually having any curtains. And so you can say to your personal assistant, I won't say her name because she's sitting right here, but you can talk to your computer who controls your smart house, and you can say, hey, girl, go ahead and close the windows. And instead of actually closing any curtains, she just rotates that polarization and everything goes dark. So lots of applications of Malice's law, and it's something like that you probably used every day, but now hopefully you understand how it works. Okay, so now we've kind of looked at our first link between what we traditionally call light, when most people think of rays of light and things like that, and the fact that light is actually an electromagnetic field. If light were just some photon, some ray that were just blasting through space and shining from the sun or whatever, we wouldn't have the concept of polarization. Polarization only makes sense if you consider light to be a wave. So from here on out, we're going to start making that transition because it is useful to think of light as being a wave or a particle. And in a quantum mechanics sense, it is a particle, but perhaps we'll get into that later. But there is an approximation to this wave called geometric optics, where we consider our oscillating wave to be simply the direction of propagation. We don't worry about the fact that it is going up and down, even though it is. We simply say, okay, I'm moving in this direction, and that's my wave front. And so instead of plotting, all the pictures, which of course I can't draw, we'll just draw that straight line showing how the wave front is propagating through space. But even though we're going to start moving into this geometric optics approximation, you can't lose sight of the fact that it is not just a ray. It's an oscillating electromagnetic field. And everything that we have learned this semester up to this point applies to light in every single case. It is an electric field, and it has that magnetic field too. So it's not something that you can ignore. So we'll get into more details about this, and you'll get to see how some effects can only be explained by the fact that light is this electromagnetic wave. We'll see you next time.